Okay. Close this, close that, close this, zoom home. Must be there already. All right, very good. Hey, oh, I love this stuff. This is so cool. So, how are we going to go ahead in example number 6 and estimate, what's it say, kids? Estimate what? Estimate what here, kids? Estimate the what? Derivative of what function? At what point? Okay, now, kiddos, I have this for you. We're going to look at this graphically in a second, okay? We'll look at this graphically in a second. I think we should talk about this numerically first. You guys okay with that? You guys over here see okay still?
We did test yesterday.
We go to 1.0001 minus 3 to the 1.
Did we get a value yesterday?
Over
3.296.
You bet. So let me ask this question numerically. Did I have the numerical part in the left box or the right box?
right.
Right.
Oh, perfect. So we actually looked at f. Did we pick h to be 0.0001? Is that
Yep.
right? So we looked at f of 1.0001. Why 1.0001? Because we're looking at an x value of what? So 1 plus h would be that 1.001, and then we went minus f of 1, and we divided by what value here, kids? Okay, now into this function, 3 to the x, what did we get for the 1.0001? In other words, we take 3 to the 1.0001 power. What did you get yesterday? Get for a value on that yesterday? 3.296 where we did this whole thing. Okay, so the derivative, or I might write this in here like the following. F prime of 1, basically saying the derivative of our function at an x value of what here, kids? Was equal to 3.296, is that right? Okay, I'm going to go with it. Okay, now I want to show you something here real quickly, because this is so cool. Desmos is such a neat tool for this, especially in calc, and you're going to start to realize that here. I'm going to jump into Desmos quickly. Kids, help me out here. What was the original function we were talking about? 3 to the x. Very good. Here's my function right there, kids. And here's the deal. Help me out here, kids. There's a point on here. And we were looking for the derivative at x equals what? Okay, now help me out, guys. If I would plug 1 in for x right here, what's that going to kick out for a y value? So do you guys agree that we're looking for the instantaneous slope at really the point 1, 3? Would you buy that? Okay, I'm going to get tricky with you. You guys told me the slope at that point was how much? What did we get numerically? 3.926. Okay, now bear with me, because this is where I get a little excited. Okay? I get a little geeked up about this stuff, and it's okay. All right. Let's label that one. What the heck? Okay. If we're looking for an instantaneous slope at a point, aren't we looking for like a line of tangency slope? And a line of tangency is a line that touches just that point right there, right? Watch what I'm about to type in. I'm going to type in y equals, I'm going to go slope intercept form with you. What was the slope we were assuming at that point? Now watch what I do here. Slope intercept form. Now guys, does that hit multiple points or 1 point there? Okay, now watch this. I'm going to write in here plus b. mx plus b form. Watch this. This is so cool. Looks like to me, and let me just zoom out once here. Looks like to me, actually, let's zoom in a little bit and make this be even more accurate. Looks like to me to make this green line be a line of tangency here, I'm going to have to move these green points. It looks like up or down to make it hit that point.
Down.
Good lordy, does that look like a line of tangency there?
Yeah.
What's the slope of that green line? Okay, the slope, now that's the intercept, right? The slope would be at 3.296 that we calculated numerically. And the idea that I can graph my original function and say, oh, my derivative here, once I take that 3.296 plus b and I add this slider in here to move that, once I see that that actually is a point of tangency, this green line only hits what point? 1, 3. It doesn't hit any other point on its line of tangency, indicating to me that the slope on 3 to the x at x equal 1, or the derivative of 3 to the x at 1 is what value? What slope did you get? Boy, isn't that cool? You guys understand this slider thing? All I did was say, okay, let's make a line of tangency to the point we're going to hit. Do you understand 1, 3? Why 1, 3? Because we were looking for the derivative at x equal what? And when you input 1, what's the output point we're looking for? 1, 3 is the point we're going tangent to. Where does 3.296 bit come from? That was our derivative computed how? Graphically or numerically? And once I knew that numerically, I said, okay, if this is true, then I should be able to put this in as a slope, put in some value b here as a slider, and move that up and down to show that, oh, by the way, what do they think the y-intercept is? Okay, so guys, graphically right here, I don't really need to tell you or draw this, but can we prove this with decimals right here? Okay, once you know your slope, put it in slope-intercept form, add a slider and plus b, and then run that thing, okay? I mean, this is, you guys have, oh, I wish I had decimals back in 1990.
1990.
Well, probably 1991.
No, 1902.
That must look good for my age.
Yeah.
All right, what questions do you have on that example there then, kids?
Why did I write down 3 to the 1.0001 power minus 3 to the 1?
So this f of 1.001, do you get that? That's like the f of a plus h. To evaluate that value, we've got to plug it in. What is your function x, f of x?
3?
3 to the x, right? So what are you plugging in for x the first time? Well, it's 3 to the 1.001, right?
I was just wondering, it made sense this time, but I just didn't know. Because what I had written down equals 1. So it's just interesting.
And graphically, once you've come up with something numerically, can you prove your work with graphics or decimals in this case? Could you?
Yeah.
Okay. Now kids, let's just assume this. I'm going to take that graph away over here. We're going to talk about this in a little bit different way. So there goes my graph. It's gone. Okay. You guys agree that this is still 3 to the x, right? And the point I'm concerning myself with is still 1, 3, right? And I would like to know what the slope of that point is, or the instantaneous rate of change of that point is. So here's what you need to do. Example 7 is tied to number 6 right here. And what they're asking you to say is this. They want you to write what, kids? Write equations for tangents. Well, guys, this is what the first derivative at that point tells you. You already know the slope is what, kids? Okay, so I'm going to write this right down here, kids. From example number 6, comma, f prime of 1 was equal to, what was it, 3.296, kids? Okay? That just simply means the slope at 1, that means the slope at 1, 3 is what? When x was 1, what was your y value, kids? Three, right?
Example 6.
Okay? So from example 6, we knew that f prime of 1 was equal to 3.296. They're saying, hey, I want you to write an equation for a line of tangency to my point 1 comma 3 such that it's tangent to the function 3 to the x at that point 1 comma 3. Well, here's the deal, kids. Do we know the slope right here? Do we know the point I want to pass through? So for your tangent line approximation, see where it says write a tangent line approximation up here, kids? You ready for this?
Yeah.
Okay. Here's how you're going to do this. You're just going to use point slope form. Your tangent line approximation, kids, is basically the following. It is going to be y minus y1 equal to m times x minus x1. So let's come up with an equation for that line. What point am I passing through for sure with that line of tangency? 1, 3. Okay. So let's start this. Y minus y1. So y minus, what's the y value of the point you're traveling through? Yep, y minus 3. That will equal, all right, what are you putting in for the slope at that point? We already found that, didn't we? Times x minus what, kids? Okay, now I could leave this in point slope form. I think it would be a good idea for you guys to probably go ahead.
Solve.
Yeah, I think we should distribute on the right and then maybe get y alone. So let's see what happens here. So you guys agree this is y minus 3 equals 3.296 x minus 3.296. How much you can add here, kids? Okay, so I've got 3.296. Let's see, this would be minus, oops, I forgot the x, didn't I, kids? Minus 0.296 when I add. Okay, we think that this is a pretty good tangent line approximation. Should we check and see if we're right? By the way, do you remember what that slider value was on D? Negative 0.3, wasn't it? Isn't negative 0.296 pretty darn close to that negative 0.3? Well, let's just type it in. Let's see what happens. What do you think we came up with for an equation here? What do you guys think? Pretty darn close to a line of tangency. Would you guys agree with that? You know, and maybe, I don't know. We did exactly 1 comma 3. I don't know. We're going to be pretty gosh darn close. I know that.
Just say it.
Pretty much the same thing, but are we there?
Yeah.
And the reason we're off a little bit is because of what?
You put the impact minus it throws.
Oh, 0.26. I want 0.2, even better. Thank you, John. How about that? Does that look even better?
Perfect.
I'd say we're pretty gosh darn good, wouldn't you? Okay, we are fine. You know why we're fine? Because we're that good. Okay? Now, I don't know what to tell you guys, but do you understand what I just did there? The first thing we found was a what? And that comes from your approximating numerically a derivative at a point. And once you have that derivative at a point, once you know the slope at a point and you know the point, what can you use to write a tangent line approximation? What formula really? Point slope form. Okay? Alright, so I believe we're at example 8. Is that true, kids? Alright. Let's talk, guys. Finding derivatives algebraically. Okay? I'm looking for the derivative of f of x equals what? At what point? Got a question for you. What do you think we're going to let h equal? So here we go. We're going to consider f of, what's the a value here, kids? A value is 2, so we're around the x value of 2, f of 2.0001. Are you with me? Okay. Minus all over what? Okay.
It's almost like it's like that every time.
It is almost. Okay, let's see this. Anybody willing to put 1 over 2.0001 for me and then run your values the length of your window in your calculator?
Why so tight?
So we're doing 1 over 2.0001, right? First, is that right?
About like 5.
Yeah, we'll pick it up here in a bit, okay? Let me pause this. Oh, where's the pen? Enjoy lunch.
Or literally,
You get.
We're doing 1 divided by what first here?
Wait. 1 divided by
0.0001, is that right? Okay. So I'm going to carry that out in about maybe, I don't know, 6 to 8 places. Is that okay?
Yeah.
And then, well, I guess that we can go ahead and make this even easier. That's going to be your f of 2.0001, and you're going to subtract f of 2. And you guys know f of 2 will be what value? 1/2, yeah, plug in 1/2. So can I do the minus 1/2 part right now? Is that okay? Okay. Now what are you going to divide that by? 0.0. Oops, I did something wrong, kids. Let me, where'd I go there? I did that.
Divided
Yeah.
the 1/2.
Okay. So I'm going to clear this. I want to do the 1 divided by 2 point. Is that right first for f of a plus h? Now we're going to subtract 0.5, is that right?
Yeah.
Because that's the f of 2. And now what do I want to divide by? What in the world is going on here? Oh, it's in scientific notation, I see. What do you guys get for a value?
It is 0.24998.
So you guys okay if I go negative 0.25 there? You guys okay with that? Negative 1/4? So we think that when we do this, 1 over 2.0001 minus 1/2, that's f of 2 all over 0.00. We get what value? Was it negative? Okay. Guys, let's just do this. We know the slope at that point is going to be how much? Negative 0.25. What point are we passing through? 2 comma what? Point what? Plug in 2, what's the y value going to be? Half, right? 2 comma 1/2. I'm just going to do some calculating down here. You don't necessarily need to write this in. We found the derivative already. We know it's going to be what? Okay, so help me out here. Let's, I would say y minus y1, which would be y minus 1/2, is equal to your slope, negative 0.25, times x minus 2. Okay, check this out, kids. I've got y minus 0.5. I'm writing a tangent line approximation here, minus 0.25 x. Boy, this is going to become plus, what's 1/4 of 2? Half? So it looks like if I add the half here, do you guys agree my tangent line to that point for our function 1/x is going to be negative 0.25x plus what? Right? Okay. We better confirm this. You know the derivative is what value again, kids? Negative 0.25. And I could be done right there, but I want to take this further like we did with decimals and just kind of confirm this. So we know, kids, that our function is 1 over what? And the point, the a value we're concerned about is 2, but that point's only 2 comma 0.5 when I insert this. So remember my equation for my line of tangency. Kids, what was the function to begin with? So 1 over x, is that right? Here's that function. What point are we really concerned about? X is 2, so that was 2 comma 0.5, right? So there's that. What did we come up with for a tangent line equation there? Plus 1? 2? 1? Wowzers. Do you think we nailed it?
Yes.
Does that green line look like a tangent line at 2 comma 0.5 for the function 1 over x at 2? I'd say we're spot on. Okay? So kids, what's the derivative or what's the slope at that point? Okay, how you feeling about this?